my new topic is a thing that I've wanted to do for a really long time and never gotten around to, which is in class 4 cellular automata, which is in fact what we were just looking at, there is the code 20 cellular automaton, which has which we can just run. We'll just run it. It's a second nearest neighbor rule. There is the code 20 cellular automaton. And you see it's the first one, the first class 4 cellular automaton I ever studied. And it has, and I looked for a long time for persistent structures in that class 4 cellular automaton. And I found these structures. So there's some structures which just become periodic. There's some structures that kind of tool across the page. And that's it. That's what I found. And then I had this procedure for finding very big structures. But the question is, what is the complete spectrum of these structures? So why is this interesting? Well, partly it's kind of a test run for discovering particle physics in the computational universe, so to speak. These are like the particles of the system. It's also interesting if you're interested in things like origin of life and so on, because one of the things that I found interesting was in some other systems a bit like this. Let's take a look here. Let's see what we have. Yeah, this is another one of these rules where most of the time the thing remains of most of the time it kind of just stays a fixed size. It just has these gliders and things. But then there's this, at a certain initial condition, the 115,000th initial condition roughly, you get this totally boring kind of tumor-like thing that starts up. You know, it's been doing all this interesting stuff, and then suddenly when there's this little initial condition, it kind of develops a sort of more primitive form of life, so to speak, like a cellular automaton tumor in a sense, that can eventually take over the system. So that's kind of an interesting analog of lots of different kinds of things that can happen, but I never found anything like that in code 20. And in fact, we have in the data repository, I put the results from code, I put the initial conditions, let's go find them. Yeah, there we go, persistent structures in the code 20 cellular automaton. So let's go pick these up, and let me show you what I want to try to do. So the goal here, so let's get, these are the persistent structures. Let's read them in. Okay, let me just make my initial thing here, code 20. Okay, so let's just look at code 20 just in the wild. So array plot, cellular automaton. Code 20 would be a 22, 2 here. And let's say random integer 2, comma, let's say 500. And let's say 300 steps. And let's make an array plot. What did I do wrong? What did I do wrong? What did I do wrong here? Since position 1 of the rule specification is not a functional rule, its position 2 must be of the form. Oh, maybe it's that. No, you know what? I should actually read the documentation. Shocking idea. Okay, so this says, oh, yeah. Rule number, yes. It's this, I think. Oh, come on. What am I doing wrong? So let's see. General rule with nearest neighbors. Let's see. Totalistic. One thing I could do is just use the. It's a two-color cellular automaton. Yes. Ah. Brilliant. Thank you. Yes. Okay, so this is an initial condition in the wild. And one of the things that's sort of interesting for origin of life-y type stuff is, you know, if you had a sufficiently long initial condition, would you eventually get some weird structure developing that would like take over the universe? Right? It's not obvious either way. I mean, but anyway, this has one particular, in this particular run, we had one glider that got one persistent structure that got produced. Let's imagine we do let's say 2000 across. Okay, so there we've got a few little structures that got made, right? So most of the time, you just get these little bell-shaped things that, again, I would really like to have some kind of, if this was natural history, what would we call these things? It'd be like you go onto this random island in the Galapagos or something, and you find these, these are really common. They are the, is it a lizard? Is it a, what is it? What does one call this? Because this is a pretty common structure that one sees in cellular automata, these kind of bell-like things. And maybe we do, maybe we start giving them names like pincers and bell and things like this. That's what's happened in the game of life thing, is that everything has some weird name that is supposed to be reminiscent of actually, that's an interesting example, because I've been interested in this question about sort of the theory of abstraction. Maybe Sweet can make a note of that, because the naming of things and things like the game of life by analogy with sort of real world things. Okay, but in any case, we've got all these things where we get a structure that is produced, and the question that we have is, what is the set of possible persistent structures? And so, in fact, we were just doing something with our other cellular automaton that was quite reminiscent of that. So in other words, if we just say, let's just start producing all possible initial conditions, what am I doing here? So these are integer digits, n, 2, 0, and then let's say we go 100 steps here. And then for each of these, we are producing, so table n goes to 200, for example, and then here we can do this find transient repeat. Now what's going to happen with that, find transient repeat, the gliders, okay, so the first question is, can we get, can we discover the things that become periodic this way? And I think we should be able to. Let's see, find transient repeat, let's ask for it to repeat 3 times. Okay, so what this is saying is, for which initial conditions, so most of these initial conditions, if we say counts of last of that, so that's saying that most initial conditions here have become periodic with period 1, probably because they're just blank. 2 of them become periodic with period 2. 1 of them becomes periodic with period 22. So if we keep going here and we simply ask, we can probably rediscover the basic structures. Let's see, if we try going out here, let's say for 5,000 of these, and then let's just go and say last of that. This will tell us what the period, hopefully tell us what the period of the thing. Okay, so mostly we've got a bunch that, okay, this is interesting. Okay, so this here is giving us a map of what the final state is from all of these. So if we just do a counts on this, it will tell us that 100 times we get a period 2 object, 105 times we get a period 22 object. The period 22 object, I suspect, was, well, let's see where the period, I think the period 22 object, we've got it here. It's the initial condition 195, produces a period 22 object. Now, the difficulty is that we are going to get some objects. So let's take a look here. There are things that didn't stabilize, which are the interesting ones, because anything that stabilizes, we know it's just periodic objects. And so although there may be some new periodic objects to be found, but let's take the ones that didn't stabilize. So let's say the position in this big long list here, where was this? In line 79. Let's say position in line 79 of 0, and flatten that out. And then these will be initial conditions that didn't stabilize, and let's find out why. So let's make a plot there of each of those initial conditions. So here we go on to say plot label is the thing, and then here we want to say integer digits of the thing, 2, 0, 0 there, And for each of these, we want to see what did it do. Let's go to 100. Let's go 100 steps. 100 steps. That's fine. Okay. Well, there's a lot of. Okay, so that was a glider that got off to a weird start, but fundamentally, all we're seeing here is two structures. Well, two structures. Two basic structures. One going left, one going right. So the question is, so we're looking, this is particle physics. We got particle collisions or whatever. We're producing particles. All we're seeing is pions or something. And the question is, can we see an eta particle or some exotic thing like that coming out? And so far, all of these initial conditions up to size. So this is all initial conditions up to size, up to number 5,000, do nothing very interesting. And notice here that in this list, like at initial condition 125,000, we have a period 38 object. So, and clearly up to size. So it looks like I've looked systematically up to size 1 million, maybe a little bit bigger than that. These bigger ones here are from doing this form of analysis that allows you to compute whether there is any structure for a given period, starting from a given period, whether there is a structure, that any structure of any size that exists with that period. And we can probably make something that will compute that now. But I think the thing we want to do is to try to figure out so here, we've got nothing interesting. What we probably should do to figure out, so for these, we could discover their periodicity. Well, we need a systematic way to search for whether we've just got one of those kinds of gliders. Maybe what we should do to begin with here is just search. I don't know how long it will take us to search, and whether find transient repeat is the right way to do it. But I mean, we could go ahead and search through. Let's try and search through. Let's say this may be crazy. Let's try and search through 1 million initial conditions and just say, let's call this periods, and let's monitor that. And this may be super boring because it may go super slowly, but let's try this. So this is now asking for, why is this not working? Why is it not monitoring that? That's very odd. I'm going to stop that for a minute. And let's see whether, if I put the monitor there, is it going to help? Oh yeah, there it helps. Well, this is okay. You know what? Mistake. I was going to have it print the thing out. That is a big mistake. Okay, so this is now scanning through. It's scanning through initial conditions. Now, I'm hoping that we have access to many more computers. Do we have access to many more computers? Okay, do I have to figure out how to do this myself? If I go to another computer here, and presumably I can at least get command line access to those, to many more. I'm trying to access at least my home computers because I have a bunch of 12-core computers, maybe even 24-core computers, whereas this is just a tiny little laptop that I'm running on right here. So we can do much bigger searches if we have access to more computers. So what is the story with getting access to more computers?
Roger has been working in touch with our now.
And he's failed.
Yes, and Raj.
I don't understand. That doesn't seem to make a lot of sense to me. This should just work. Maybe somebody can tell me. Maybe you can tell me what exactly has gone wrong so far. Why that isn't working. Okay. In any case, let's go back to this. Well, we're at 100,000. I don't know whether we can sort of tell Actually, the one thing we should have done, boy, this was stupid. Even on this machine, I have 2 or 4 CPUs. I should have run parallel table instead of just ordinary table. But I should be able to just run this command on my very worst case. I should be able to just run this command in a command line. I mean, I should be able to connect to a remote kernel on my home machine, for example. Let's see, how do I get to it? Kernel configuration options. I should be able to connect to a remote kernel and run this in a notebook, but I suppose worst case, I can just run it as a piece of Wolfram script code. Let's see, can I run it in the cloud with, can I run it on AWS? Anybody know how I can? I mean, I'm just running this one piece of code. So this is not a, it's not like I'm trying to get, I mean, so long as I can run this one piece of code. So for example, if I go, is it going to work if I connect to VPN here? Is it going to drop my Zoom connection or not? Okay, I'm going to start, I'm going to see whether I can get to one of my home computers. Let me see. And let's try an SSH somewhere. Oh, I'm there. Okay, so I'm on a Linux machine. So this is now a Linux machine. Let's see if I can start Wolfram script on that. That is promising, very small, but promising here. Okay, so we're back to just like what the world was like in 1988. Let's see, what is the name of the, what gives us the number of cores, number of processors? I think it's processor count. 8. Okay, so that machine at least has 8 processors. It's not as many as some. So I'm wondering if I can SSH into my machine Lambda. Let's try doing that. There's kind of a theme here of these machine names, but let's see if I can SSH into Lambda. That's promising. Aha, that is very promising. Okay, let's see if I can run Wolfram script on Lambda. Okay, yes, that's all good. Okay, this is looking better and better. Okay, so let's say $processor count 12. Okay, well, we've got an 8-core machine and a 12-core machine. Okay, this is super primitive what I have to do here, but I think it will work. I can just take, I can run, actually, I should be able to use remote run. Let's go look up the documentation for remote run. I mean, this is so primitive as to be unbelievable, but the problem with this is I'm not going to be able to do this without having, well, I might be able to do this. So let's say remote run of a command, or I can copy files back and forth. This is really just like 1988. It's same exact technology.
You do SSH there. Can you just launch a remote kernel there?
I can launch a remote kernel through SSH, but the problem is that for some reason, my ability to set up, I mean, I don't see why I shouldn't be able to do this. Given this, I should be able to configure a kernel on, let's say, Lambda. So if the kernel program, it's running through, okay, I don't know why this wouldn't just work.
Why wouldn't you do parallel kernel so that you can use all of them at once?
Oh, I will do it in parallel. I absolutely will do it in parallel. But so the question is whether that will work if I now go and say notebooks kernel Lambda, and now I say 2 + 2 here. No, failed to connect. Growl. Yeah, failed to connect for some reason that is unknown. Well, anyway, we are about halfway through after I'm sort of telling the fact is let's write the correct piece of code here. And we're going to scan through for, let's do it in parallel. So this should be a parallel table. And what we should be doing here, instead of 10 to the 6, let's go between 10 to the 6 and 2 times 10 to the 6. And let's go ahead and take that result. And I want to take that result. Really what I want is I want to just take that result. That's fine. I can get a million numbers. And what I'm going to do is I'm going to put those numbers into a file called, I don't know, results1.wl. Okay, and that is the code that I want to run. And so I should be able to just take that code if I wanted to. Gosh, let's be like super unbelievably primitive. I think I can just run that code. If this works, it'll be disgusting. Let's see. Okay, I think I can just go ahead and run it there. Okay, launching kernels. So it should be launching 12 kernels on my machine. You know what I'm going to do? Let's just not live quite as dangerously. Let me interrupt this abort. Again, this is.
Also from Syscom's wondering if you change the hosting option to Lambda.
Okay, we'll try that. Okay, this was a little bit of a fail here. Let's go Control C, kill, die. There. So what I should have done there, let's just exit this. Okay, and let's hope that we didn't leave a bunch of random remote kernels up running that shouldn't have been there. But I'm just going to do something where instead of the put here, I'm just going to check that this basically runs before I start running it for a million steps. Let's just run it between 100 and 200 here. Let's just check that it actually works. Okay, or is this hanging? Oh no, there we go. Okay, so that's working fine. All right, so I can do the real one here, and I'll just leave it running. I don't think the monitor is going to do us any good. It doesn't seem to be actually successfully monitoring there, though that probably should one day work. Let's try this. Okay, so that's between 1 million and 2 million. That's running on that machine. Let's start it off, and boom. Okay, so that's going to do that. While it's working, let's go back over here. We're at 800,000. We're getting close. And we're trying to, I really wanted to, okay, and somebody had a suggestion for changing the way the remote kernel configuration works. Kernel configuration options for Lambda, edit those, and change the remote host name to Lambda. That's a good suggestion, because otherwise it doesn't have a hope. Let's try that. I mean, my poor machine Lambda is now going to be absolutely slammed because it's being used to, all of its cores are being used for a big parallel computation, but let's see what happens here. Is this going to work, or is it just going to hang? That's not very impressive or encouraging. Oh, don't tell me that aborted. Oh my God. That was bad. That was stupid. Oh my gosh. I thought that was the remote kernel thing going to Lambda. Oh, shoot. Okay, well, here, recovery. Okay. Oh, look at that. That already finished. So, okay, that was okay, well then why don't we just run it again here? So that was between 1 million and 2 million. So now all we have to do is to copy that file. So let's find out what directory we were in over here. See, that's what you get for having, oh gosh, it's in my home directory on that machine. Okay, so there should be a way of doing a remote copy. That is on, so I'm there. that machine. I think if I write that file, I know what I'm going to do here. I'm going to actually copy that file by going to, maybe if, Swede, if you're communicating with Roger, would you tell him to copy the file results1.wl into my Dropbox directory for this experiment?
Right. SCP,
Well, let's see if that works. I mean, there should be okay, let's try it. So you suggest, do you think I can do Control Z let's go. Are you thinking that I have to log into that machine first? Right. Right, but the problem is that's not useful actually, because okay, let me do that over here. Let's see. Well, while I'm yakking about all this stuff, hold on. While I'm yakking about this stuff, I might as well let it run on a different computation. Let's do something which puts out a result 0, which was the thing we just blew up over here. So let's just go up to 10 to the 6th there, and let's put that, run that over here. Okay, now I need to go and do an ls here, and I should see results 1. Let me just check that that's ls-l. Oh yeah, it's a nice 3 megabyte file. Okay, good. Okay, so then all I have to do, you say, I don't even need to do
open a new terminal and then say SCP lambda column /
no, but I'm trying to move it into a Dropbox file, so it's actually already mounted on Lambda. So I just have to know where that file is mounted, and then I'm in good shape. I wish I could just use the remote kernel on Lambda. Summer School, live coding. All right, let's just put it in here. Sorry, just a second. Okay. I just need a CP. This results 1. Oh my gosh, it already finished. Result 0 is already finished there. So that's great. Okay, let's do that. CP results 1.wl to the same thing. It was a very primitive. I mean, this stuff would all have worked 30 years ago. Okay, all right, I should have those files now. Okay, let's take a look here. So events 2018, Summer School, live coding, and there they are, results 0, results 1. Okay, great. So now, actually, while I'm at it, why don't I have this trusty machine of ours run a bigger case? Let's run it between let's run it between 2 million and let's run it between 2 million and 10 million. Just and let's not make the mistake. Let's call that results 2, and let's go ahead and run that. Okay, meanwhile, back over here, we want to read in those files. So let's call that results 0 is equal to get. And now we want to just take that file and say command I. pick up its directory. .0.wl. Okay. All right. That now gives us our. So that gives us all of the first million. So first thing we want to do is just to say counts in results 0 of just counts in results 0. So that's going to tell us how many of each. So there were that many initial conditions that just led to period 1. So we've clearly got an objective size of period 4, which occurs quite rarely. And we've also got 15,000 cases where something that wasn't, so we've pruned this down to 15,000 cases where we didn't just have things with known periods, okay? So if we go ahead and get, so let's say results equals, let's see how it's doing running that other one. Now, we can't, it's not quite finished yet, but soon we'll have the first 10 million of these guys. So now we've got results here, and we should be able to see, let's go ahead and say join results 0 and results 1. Oh, whoops, results 1 we've got to get by pulling in that file. So results 1 here. Okay, all right, so now let's just do accounts for this thing, for results. Okay, same deal. We've not seen any new structures. We've got 32,000 cases where we can't tell what happened, right? So the question is, what are those 32,000 cases? Are they all single gliders? Are they all something different? We're still in the zone where, where I figured this out in the early 1980s. I think we're going to soon get out of that zone. We're going to soon get to the sizes here, which are bigger than I've ever sampled before. So let's I mean, certainly would help if we were running on more machines, but let's see. All right, a watched computer never boils. Okay, so let's try to start seeing whether we can write automated code. So find transient repeat is probably a pretty efficient way of pruning things down to figure out whether we've still got anything interesting happening there. So the question is, if we look at the ones that have zeros here, so let's find the position in, oh, let's hope we didn't make a mistake in the seam between those two things. Let's see. The first one of those was, let's be very careful here. So, oops, not that one. Okay, so one of them was, the question is whether they started at 2 million minus 1. I don't think they did. We need to be more careful. So this was up to, okay, so in fact, what we want to do, let's be more careful. Okay, so length of results 0 should be, so that was exactly 1 million. Length of results 1 was 1,000,001. So that must have gone from 1 million to 2 million. And so there's an overlap of 1. Is that correct? So what we really want to do here is to say, join that with rest of results 1. And that should have length of that should be 2 million. It is. Okay, we're in good shape now. Okay, so, and we can just do that again. It'll be almost the same. So now we can say position in results of 0. Then we flatten that out. And we should have the 32,000 cases where we have zeros in there. And each of those should be, so let's randomly sample. Let's just take a random sample of those. Oh gosh, I didn't mean that. I meant random sample of pos 0. Let's just take 20 random samples there, and let's go ahead and do this. For those 20 random samples, let us go and just see what they do. Okay, so most of those then were, it's an interesting question. Why? So some of these were in fact repeating structures that somehow didn't get caught in the net. And other ones are gliders of various kinds. So that repeating structure that didn't get caught in the net, maybe it didn't run for long enough. We can find that out. This one here, 1140585, I'm certain is going to die out. It just didn't die out yet. So maybe what we need to do there to figure that out is to have a second level of pruning. Okay, so the second level of pruning might be to run it a bit longer and see if it, so what we're going to probably end up with here, let's see what we have here. So now let's take this and let's say, let's do this. So let's say length / find transient repeat. Okay, so last of that, that will tell us for a given one of these. So let's take this one here, 114. Oh gosh, I don't have to retype it, do I? Well, I can. Okay, 1140585. Okay, so that one gave 0 up to that length, but I reckon if I run it for 200 steps, it's going to die out. Okay, so what I probably want to do is I probably want to say select in. So the first thing they want to do is to say select in pos 0 for those ones of these that are equal to 0, for which that last of length or whatever is equal to 0. And that's going to give me the ones that aren't yet even at length 200. So that's going to give me, oops, I don't want to print it out. That's going to give me that's going to prune down by scanning through, right? So what that should do, if I didn't get this wrong, is, I'm surprised it's still running here. I'm surprised it isn't finished. That's running for 200 steps now. Oh, maybe it's longer because the 200 step running takes longer. Okay, is this still running? That is still running as well. Wowee. Okay. Oh, there we go, we're finished. Okay, so now let's call that pos 0 pruned 1 is that. And then let's say length of that. Okay, and let's compare that to length of pos 0. So we lost only 4,000 structures there. Okay, so my guess is if we take the same thing that we did up here, a random sample of 20 of those, let's take a look. I think these are going to be pure gliders. I think there's going to be nothing else. So what we're looking for is this a, okay, boring, right, they're all just gliders. So now the next thing we need to do is figure out how to recognize when one of these things is just a glider. Who has an idea about that?
You can shift the first black one, the first position. Or
yes, that's a good idea.
Trim the white parts from both sides.
That's a good idea. Let's trim the white stuff from both sides. Okay, so let's write that. So let's take. So we're going to get each. So let's take an example here. Let's take. Let's just get a sample here so that we know what we're doing. Okay, so let's take that initial condition there, and let's say we take this cellular automaton. Oops. And we have this, and our goal is, oops, our goal, now let's see, does trim, how do we do that? Is there a list trim? There are various kinds of trimming functions. String trim, how do we do this? We pad, it's the opposite of pad left. It's, No. What we want is not padding. We want
But if you pad this negative index.
No, but what we want to do is we want to, I know how to do it. It's very easy. What we do is we just use split to remove all of the, right, we take the first, all we're going to do here is we're going to say split, okay, so for each of those rows, let's just take the last row here just to see what we're dealing with here. Okay, there's what we're dealing with. So if we just say split that, it'll look like that. And all we do is to take the elements 2 through -2 and the split of that. So here what we do is we say elements, so we say split of each one of these, and we say split that elements take that 2 through -2.
The divider might be at the border, in which case it's not going to work.
I think it leaves a border. I think it always leaves a border. So let's try, see what that does. And let's say find transient repeat of that. And let's say 3 or something. What did we just do? Oh, important point. After we do the take of the split, we have to join them again. Flatten them. Now, what on earth just happened here? Okay, let's take a look at what structure we've got here. So we should have that should be a list of, well, let's see what happens here. If I say pad left of this, array plot pad left. Okay, there we go. So now we've got a straightened out glider. And why is find transient repeat not working on that? Let's see. What am I doing wrong? So this is find transient repeat of that thing. I don't understand why this isn't working.
Is it the 3 is a period? You're looking for 3 repetitions, right?
I'm looking for 3 repetitions, and it should be showing me. Well, let's just look at this thing here. That thing there should be an object. Let's check the dimensions of that object. Oh, it's not going to have dimensions. It's going to be a ragged thing. Oh, I know what the problem is. I have to do a pad left because otherwise it doesn't know how to. Yeah. I have to pad it because otherwise it's going to be. It's going to think that it is. Okay. So this now. Yeah. This should be exactly right. Length / at that. Yep, that's right. That's a period 9 glider. Okay, so what this now should be doing is, so now let's say deglided is of an integer n. This is very bad. Okay, we could call it a deglided period. Integer n is this thing. And actually, it's just the last of that we want. That's the period. And let's make it, 3 is enough. Okay.
Why do we need 3? I mean, if it's repeated once, it's going to repeat again.
You're right.
Use the same initial condition and we do the same thing.
Let's say 2. I'm just a little concerned about things with glider collisions and so on. Let's leave it at 3 for now. I think it may be unnecessary, but it's not going to, it shouldn't hurt anything. Okay, so this is now saying deglided period. So let's say in those, so let's go back here to the pos0 pruned 1, and let's say pos0 pruned 1, and then let's say select. Well, let's just say deglided period of that. Grind. Shouldn't take that long. I don't know why it's taking so long. Okay, well, it should be finished soon. And then that's going to give us, let's see how this is doing. Oh, that's finished, great. So now we've also got a results 2 up to 10 million. And why don't we, while we're at it, why don't we start it for the next batch? Okay, that finished. All right, hold on. Let's just stay organized, he says. Being kind of disorganized. But let's start this one for the next batch. So instead of 10 to the 7, let's go 10 to the 7 here up to 2 times 10 to the 7. And let's put that in results 3. And let's start running it. Okay, now here, over here, let's make a counts in %120. Okay. Oh, that's interesting. So so that's telling us that there are 5,000 cases in which we successfully which we've identified a glider at period 9. But there are still 21,000 cases in which we don't have, in which we failed to get. Okay, so let's say select. Let's see, in %120, we want to say extract in pos0 pruned 1 of the position in %120 of 0. And that should give us the, so that's pos0 pruned 2 is that. So that should give us things where, so that should give us cases. So let's just take the first 10 of those. And now that is very funky. That is very funky. Let's see what's happening here. Something went wrong there. So those are cases, I have a suspicion about what happened there. So these are cases in which we failed to, okay, why are those? So those things we should have, so let's try deglided period. We have a bug here. Deglided period of 187 is 0.
Could it be that it hits the border and then starts again?
No, but it could be that it has.
No, I mean after padding and trimming.
Let's find out. Okay, let's find out what happened here. Let us find out. Okay, so here. Oh, okay, so 187. And let's do an array plot here. Oh, look at what on earth happened there? That's really weird. What happened there? All right, let's see what you must be right. You must be right. It must have hit a border. It must be that I'm actually wrong about my claim. So what we have to do to fix that in a bit of a hack is we can just say in here, join some zeros. Join 0. We just want to pad the thing with zeros on either side. Okay, so now let's try the same thing again. Oops, I don't want that. I want, well, I could do the same. I could just use the same piece of code just to see what it does. Ta-da, looks better. Okay, all right, so let's try, this is now our deglided period again. And let's do, let's run it again here. Then this may kill everything, we'll see. Let's see here. And let's see how this one is getting on. You know, while we're yakking away, the computer is computing. Okay, so we've also got results 2, which we can pull in and follow and do the same treatment there. And I mean, ultimately, what we want to do is run this on 1,000 machines or something. Okay, here we go. Okay, great. So there were the 9 structure occurred 23,000 times, so we're down to 33 cases where there's a 0. Okay, so let's do this. And let's say pos 0, prune 2. So now we're on the hunt here. So those are our 32 cases. And I reckon these are all going to be pathologies of some kind. Let us see what they are. Aha. And therein lies the beginning of our problems. Okay, so these are all multi-glider configurations, or mostly multi-glider configurations. So there are a few that we just didn't run long enough. But mostly what's happening here is that there are 2 gliders in the picture. Okay, so what we need to do now is, so now we've got one piece of pruning code that takes a result. And so we've got to try to organize what we're doing. So the first step, let's make some notes about what the, what we're trying to do. Okay, so pruning procedure. So step 1, which we did, was we're going to say use find transient repeat. Well, actually, what we're really trying to do there is identify pure periodic results. Okay. I mean, probably okay, so that we know how to do that. The next step is identify pure glider results. So this is basically use find transient repeat. This requires use degliding to get that. Okay, so this is now okay, so the next step is going to be identify multi-glider results. I had really old code from the early 1980s that did some of this stuff. It'd be fun to run it again and see what, I'm sure it still runs. But I think we can do it more efficiently here. So the question is now, how do we pull apart these things with multiple gliders? And I would assume what we have to do is to wait for a while until they have enough white space that we can that we can separate the 2 pieces. So let's take a look at the sample of one of these. Let's take a look at the first one of those. It's suggesting on the live stream, why not use machine learning? I don't think it's going to work. It's I think this is sort of a case where you have to, well, again, I think it's easier here to just try and find the white space in the middle. So 911,999, let's go look at that one. And let's see how we do it. So I think what we would do, what was it again? Was that first one? Okay, so, oh, come on, what I want. This thing here. So there. Okay, so this is our thing. And now what we want to do is, at the end of this, we want to figure out where there's a big run of zeros that we can chop it. So we want something where we say, I think what we want to do, so let's take the last of this, and then let's say split that. And now I think what we want to do is simply say, where is there a long run of zeros? And then we break this into 2 separate sections, and we evolve both of those sections, I claim. So I think, again, let me think. So we want a run of zeros how many zeros do we think is enough zeros? Let's say 20 zeros or something. Well, let's say cut at zeros of a list. And then that would be split the list. And then what we want to do is we want to say, in that list, we want to say position. This is getting a little weird, but let's try doing this. Position in that list of a list which is 0, ... and where the length of that list, question mark, length of hash is greater than, let's say, min here, an integer. So this is now asking for the position of places in that list where, so now what we want to do is we want to somehow cut the list at those positions. And we have this new function called take. There's a new function which takes at a series of positions. What is it called? Take. I think we have this. We have a thing where you are, what is it called? Where you have a sequence of I think it's a new function that made it into the latest version. It's something where you're chopping a list up, and I'm really disappointed that it's not in the C alsos here. Why isn't it in the C alsos? Maybe because it doesn't exist yet in the system. I thought it was a thing that would chop a list at a succession of different, values. Well, okay, so look here, we can at least do this. We can say cut at zeros. What's it called?
Just maybe some sort of partition.
Yes, right. I mean, it's a, I wonder whether that's, okay. Oops, cut at zeros, let's say 5 here. Okay, so that says there's at length 7, at position 7, there's that cut. So what we want to do is we basically want to cut this list at every position. So what we want to do is to say flatten this, flatten all those positions up. And then what we want to do, so there may be multiple gaps between these gliders. And we can simulate this by trying a state with multiple gaps. But basically there's going to be various gaps between gliders. We're going to want the final state. Okay, so my idea is to wait until we've got a long enough sequence here and then cut the thing up and then re-evolve the pieces and see whether the re-evolved pieces are just gliders. That's the idea. And
is it take list?
I think it is take list. I think you're absolutely right. I think it is take list. And, is anybody here who could make a note of, let me make a note of take list should be in the C alsos of take. Okay, so take list by successively taking NI elements from list. Actually, that isn't, after all of that, this might not be exactly what we want, is it? So this is, we've got the position in here of each one of these we've got the position of each place where we want to chop this list. And then we want the values. See what I'm saying? We're trying to chop up this list where we get all the elements before this big long sequence of zeros, all the elements after the big long sequence of zeros, and we may have many of these. So, I mean, just simulate, just for fun, let's simulate what it would be if we had many gliders all together. So we take this list and we could just say join that list, so join the list to that thing with a bunch of zeros. Okay, let's do that. Okay, so this is a simulated line 143 is something. So if we say cut at zeros of %143, we should get, comma 5 or something. We should get, yeah, okay. So those are the places we want to cut that list at. So now the question is, how do we? Those are the splitting points at which we want to cut the list. So, and then we say split %143, and now we want to cut it. So we want to remove elements. Want to remove these elements. I wonder whether riffle will do that. Will riffle do that? Will riffle split at particular points in which every nth element is x? Does it split at points?
Can we do sequence split?
What's that?
Can we do sequence split?
Let's try. That's a good idea. Sequence split. Oh, that is brilliantly correct. Yes, that is right. Into sublists separated by sequences that match the pattern map. So in fact, the correct way to do this is to use sequence split here. That's going to work. So sequence split of that original list, of the split of the original list. Okay, so I think you're right. So let's do this. Okay, so cut zeros. Okay, so let's now do of line 143, cut at zeros, line 143, 5 times. Okay, now what has this done? Length, hump. What did I get wrong here? So this is the original split, and now what I want to do is let's see. This, what did I get wrong? What does it do? So it sequences that match the sequences into sublists. Oh, I don't even need to do the split here. Yeah, okay, so let's try that. Brilliant. Well done. Yeah, that just worked. Okay, that was extremely easy. So that's just cutting at, okay, so all of this is garbage. So that just, except let's not get rid of that test case there. So this is just saying at, yeah, so all of that is irrelevant. That will just work. Okay, so that now, so our third pruning step just involves separating everything into, so cut at zeros, and then each one of those has to be padded and treated as its own evolution. So then we do the exact same thing as we did up here. So then we just ask for deglided period of, okay, so let's do, oh, and that even has those little padding things on it. So in fact, deglided period, so what we do is cut at zeros, then we do from digits 2 of that. All right, so let's take our remaining ones. These were the ones here, pos 0 pruned 2. So let's take, okay, so this is now pos 0 pruned 2. Those are the ones that still survived. And what we want to do is cut at zeros. And let's use 5 as our size there. And now let's say, and each of those is from digits hash comma 2. That will turn that into a list of numbers. And then what we want to do to those is we want to say deglided period of each of those, I claim. Let's just do this on the first 3, just before we tempt fate even more. Okay, it didn't work. All right, let's see what went wrong. Okay, so let's say, I think maybe, oh yeah, I know what went wrong here. Cut at zeros should be integer digits, comma 2 there. Humph. Okay, that wasn't good. All right, so let's see what this is doing. So each one, so cut at zeros. So first of all, let's try cut at zeros. So what's the first of pos 0 pruned 2? Okay, that's that thing there. So let's do this. Let's cut that. Okay, so for some reason, 911999, how can that be? 911999. Oh, that's, I see what's wrong. I see what's wrong. Okay, very stupid problem here. That integer digits thing, that's the wrong thing to do. What we actually want is the cellular automaton evolution from that. So cellular automaton, oh boy, okay. Okay, so we need to take this in there, and we need to do this. There. We're trying to get the cellular automaton evolution, but we're only trying to get the last thing there. So that is, so let's try this. Blah. Okay. All right, so let's try this here. So this is now for 911999. Okay, well, that's the wrong answer, but that's, oh, I see what we need to do. Okay. Okay, now we've got a reasonable answer. All right, so let's go back and put this in there. Oh, boy. First of that cellular automaton evolution. Sorry, here. So that was, okay, there we go. All right, so what that's telling us is, it's great. Okay, so what that's giving us is for each of those pruned things, it's telling us that it's a 9 glider and a 2 glider, and that's all there is there. So we can do the whole thing for pos 0 pruned 2. Okay, and everything is dead. They're all just gliders. Right? That's it. That's the, so up to size 2 million, we just verified that nothing else happens other than just gliders. And so now we've got our results 2 and results 3 are both done. So I have to copy them over here. Results 2. Okay, so now basically we can repeat this analysis on those next 2 cases, which go up to 30 million, initial conditions up to 30 million. And probably what we should do is just leave the thing running. Let's do results 4 here. And may as well just leave it running, going from 2 times 10 to the 7 to 3. Let's go to 4 times 10 to the 7, just to be a little bit more ambitious. And I want to go over here. Okay. So meanwhile, I can do my same stuff that I did here, where I just read in wherever it was. I've got the slight trickiness of remembering which, so I've got my whole results list, and gosh. Okay, so let's read in results 2 and results 3. And again, there's some trickiness because we are at, it's kind of silly, but results 2, results 3. The problem is that we've got these offsets about which numbered initial condition each thing corresponds to. But let's at the very least find out let's at least get counts for how many of each kind of structure there were in each of these. And so we need counts of results 2. Oops. Okay, so there are 139,000. Let's see, in results 3, we still don't have any different periods showing up, but we've got a solid 300,000. There's 300,000 cases that are either gliders or something more complicated. So, gosh. I have a feeling that this is the point where it gets a little bit grindy because we have to basically just keep iterating this. And what's going to happen is eventually we're going to end up with cases that we can't resolve, and we're going to have to do more and more levels of pruning. So we're going to have 2 gliders, then we're going to have probably multi-gliders is all we're going to see for a while until we start seeing something more elaborate. I mean, that's, presumably there's something more elaborate out there. And that's what we're looking for. And so right now we've got to, we've got to 10 million initial conditions. So up here, so I don't know what it took to find the period 5 thing. I don't know whether that was found by going backwards. Let me take a look at the AKS book because I bet that will show what was going on there. Let's see. Structures in class 4. Here we go. Okay. So I see. I think this was as far as I got with direct searching, was 256 million. So, oh, actually, this claim here is, wow, that was a long, oh, I guess this wasn't that long ago. This was probably around mid-1990s. So shows all the structures I found by explicitly looking at evolution from the first 25 billion possible initial conditions. So we're still, we're actually kind of modest right now. We're only looking at 30 million. So we've got, another, so these probably ran for a while. I mean, obviously they were running on computers from the mid-1990s, but the claim is that these are the structures that I found. And this was at 14 million, you start seeing apparently this glider that propagates with, this is a period 2R glider. There were some period 4 things, which we should have seen already. Those were at, so let's take a look. Did we see the period 4 creatures? Yes, we did. We did see some period 4 structures. So we've seen basically up to here. And we will see in the pile that we were just making, we will see this guy. So the question is, can we get beyond 25 billion, and what happens beyond 25 billion? Because the next things I saw, well, that's kind of a downer that I managed to get to 25 billion of these. So these are the things with small periods up to 10. And the period 3 that looks like the first period 3 thing occurs. That's interesting. That kind of gives a lie to the claim on the previous. Oh no, 25 billion. This appears at 222 billion. That's the first. That's a period 3 object at 222 billion things, and this is so. There's okay, and that period 5 object occurs at 22 billion. And then these ones are up in the trillions. So, and there's one there at 10 trillion. There's a period 8 thing at 10 trillion. But the question is what, when does something that isn't like this occur? And I think we have to, I'm afraid we probably have to declare defeat here because I don't think we're going to be able to get, because we didn't get, I was hoping we would have access to 1,000 machines, which would have allowed us to go a bit faster. And I mean, as it is, we're only running on 12 machines. So a factor of 100. So I mean, just to give us a sense of that, these computations here were taking, I don't know, let's say 10 minutes. So at 10 minutes for 10 million. So let's say 10 to the 7, 10 minutes is 600 seconds divided by 10 million. So that's the time per computation. So let's say we want to get up to 100 billion. 100 billion times that is otherwise known as 6 times 10 to the 6 seconds, which is otherwise known. So let's divide that by 1,000. If we have 1,000 cores, that's 6,000 seconds, which is a very modest amount of time. That's 100 minutes, which is less than an hour and a half. So with 1,000 machines in an hour and a half, we could get up to 100 billion. And then the main thing we've got, and I think we've now got the code to do all pruning, all known pruning. Since I claimed that up to 25 billion, the only thing one saw was a bunch of gliders. So the code we've got will prune everything up to so if anything survives the code we've got so far, then it indicates that there is new physics, so to speak. But the problem is we need more machines. Now, the other possibility, we could run this. There is a network of 700,000 machines that we happen to have access to. That is a thing called Charity Engine, which is a strange crowdsourcing, SETI-at-home-like network. And actually, they've always wanted us to run some science thing on those machines. So I think we actually can make containers and run computations on that machine. So that would be a good thing. So the thing that I've been doing here, I mean, it's a very tiny piece of code, which is good. So this is the first level pruning. The second level pruning could be done. Probably what one wants to do is collect. So okay, so let's estimate the number of. Let's just estimate the number of. So this is the number of zero objects in that set of 10 million initial conditions. So that's 182,000. So interestingly, the number of zeros increases slightly as you go from the first 10 million to the second 10 million. And that's probably because the number of multi-glider initial conditions has increased slightly. So this is, so here we've got, so let's just estimate 182,000 of those divided by 10 million here. So that's about 2%. So that implies that of the first 100 billion, we would get, with 100 billion of those, we would get, okay. So we then get 2 billion, yeah, obviously, we get about 2 billion. So our pruning is also going to have to be done in parallel because we're going to get, of the 100 billion, the first level of pruning, yeah, what we're going to have to do is write a piece of code that will do probably all levels of pruning together and basically report in. What we'll want to do is report every time we find a new glider that we've never seen before. We'll want to report that. It's actually one thing we're doing, which is wrong, is we're assuming that just because it has a period that we've seen before, it means it's a glider we've seen before. We also might want to figure out, what other particles exist even before we see exotic new physics of things that aren't just pure particles. But I think that's what, yeah, that's the thing that. That's what we would have to do, and so all the code that we've got here, we should package up. Yeah.
How we can decide about the number of fives? Like we set it equal to 5. Was it a good number?
Oh yeah, that's a good question. So the question is, why do we think that 5 zeros is enough to separate gliders? It's a really good question, and it could be wrong, right? So, but you know what? It's a self-answering question, because let's say that we break it. Because there's a thing with 5s and 5 things in the middle. If the pieces don't turn into pure gliders, then we know something went wrong. Right? So in other words, let's say we take one of these structures, and in fact, let's say we broke it there. Okay, then each piece is that really right? You know what? You might be right that there's a problem.
I think we need to check that the gap increases after one period.
Yes, that's right.
In that case, it has to be
right. So we made several mistakes so far. Okay, so this is where did I put this? Okay, so mistakes so far. We are assuming that gliders of that structures of the same period are the same, which is not correct. Second, we are when we split gliders, we split states as having white space between gliders. We should check that the white space increases. Now that's going to get tricky. By the time we have 3 gliders, we're already going to have something tricky going on there.
Oh, the shades, it's not decreases because it might stay the same.
Yeah.
Yes, okay.
And it's between each neighboring pair of gliders.
Yeah, it does not decrease between any neighboring pair.
Oh, they might collide, but we could just wait until that happens.
Well, if it does decrease, they could collide. And then,
Yeah.
but I mean, the number of cases where weird things are going to happen is going to be fairly small. And then we want to prune and look at those weird cases and then find out how to prune out those cases if they're not interesting.
So what's the meaning of the collision? The other case was, a new particle. The collision, does it mean anything?
Well, it could mean that a collision could occur if multiple gliders. Actually, can that ever happen? So can there ever be a collision? So in here,
It can be if the speeds are different.
Of course,
There can always be.
you can just have different initial conditions.
yeah, but if you move there can be a collision if you just move the gliders far apart, and then they collide. But I don't think that can ever be. How can that be interesting? How can that make something? Okay, so one problem that we have here is it's hard to imagine what we can make. So, for example, in that other case of the 1329 rule, I never guessed that would make a structure that was just a fixed growing structure. Just didn't imagine that would be a possible thing that could get produced. So here, the most likely thing that would get produced is something which is essentially a glider gun, where there is a fixed structure and it emits a glider periodically. Now, much more exotic things could happen. It could emit gliders aperiodically. It could be a structure that just grows. And the question is, can you get, in any case, can you get a situation where you've produced gliders, they collide, and assuming you evolve it for long enough, can you ever get, I don't see how that can happen. I mean, if you started off, I don't see how that can ever happen and be interesting. I think the most likely thing that's going to happen is, oh, you know what? We've already made a mistake here. We've made another mistake. Okay. The next mistake we made is we will not detect glider guns properly, because what we actually have to do is we have to run. So in other words, let's look at the case where there was a glider gun. Wherever it was in the book. Let's see. Okay, so let's say here. So we're happily going along, and this thing is effectively a glider with a giant period. Okay, so we're all happy there. And then suddenly, ta-da, we get that thing. Now, in the detection, I guess, no. We would detect this. I'm sorry. We would detect this. The fine transient repeat will never say that this is periodic, because as we evolve further down the page, it's just going to be different. So we wouldn't miss that. So. Yeah, and I mean these are just totally weird things that I never thought would happen in a rule like this, and that's what probably will happen somewhere in code 20. I mean, one sort of claim might be that in any class 4 cellular automaton, there will eventually be structures that grow without bound. I don't know if it's true. I failed to find it for code 20. I mean, I could if it might be worth looking at the old 1990s code that I had, because I did put some effort into. I actually think this code was from the 1980s. Now that I think about it, I think it's really, really antiquated. I think it's really, yeah, we probably shouldn't look at it. It's probably horrifying, because it's probably full of heuristics. Because it was written. Yeah, I wrote this code originally. It must have been in 1983. And I wrote code originally in 1983 to do this, and it was probably it will have been written in C, and it will have had all kinds of heuristics that I put in over some period of time with all kinds of horrible possibilities of error. But anyway, well, so sadly, let's see whether our other thing ran here. Let's just see. No, it's still running. Okay, so we're still running the up to the 40 million case on my 12 processor machine. But I think it would be fun to actually run this on more. Let's just imagine that we could run it just for fun. Let's see what it would be involved there if we ran it on the machine on the 700,000 processors. Then clearly, well, yeah, we get a factor of 700. But okay, but so we have to prune. We have to have something which does much more pruning. I think we can do all the pruning steps we've described so far. None of those will cause trouble, and see what gets left over. And well, we should probably wrap this up. Unless other points, yeah.
These patterns, do they correspond to anything in reality except particles?
Is there a significance to these? I don't think they really correspond to. I don't think these correspond really to particle physics. They are a metaphor for what happens in particle physics. I mean, in my current belief about how this might actually work, it's all on these networks rather than on discrete lattices. I think the other case that's sort of interesting is it's a metaphor for this origin of life business, because it's kind of like, this is a metaphor for, do you get some weird combination of atoms or molecules that will produce something which, for example, can replicate itself? And that, that thing that I was showing, where you might have said, oh, the chemical reaction would just blob around and be periodic, but actually there's a case where the thing will, produce more and more copies of itself. So I think that's so far as I know, the main interest is metaphorical, although, the other thing is doing computation for these things. So like proving the universality of code 20, which would be something that one would need. I mean, I don't think anybody has really seriously tried to do that, of taking, yeah?
Can I rephrase my question a different way? Let's say that these patterns, they represent the physical system. That physical system is an isolated physical system, or is it a system can interact with an environment?
Well, I mean, in this case of this, you're asking about whether if this represented a physical system, what kind of physical system is it? This is a very idealized, precise physical system. This is not a physical system with, there's no noise.
It's isolated.
Well, yes, it is the physical. It is what we are looking at is the complete system. It doesn't contain, there's nothing outside the system that we then have to, start talking about, extra effects and so on. And I think so. I mean, I guess my I think really this whole phenomenon of it reminds one a little bit of number theory, in the sense that it's like, does there exist, is there a solution to this equation that says, for example, in the case of these glider-like things, it's basically the equation that says that the nth power of the cellular automaton operation is the identity. Because if you have a glider, it's saying you apply the cellular automaton operation, the glider of period P, a persistent structure, something like this. If you apply the cellular automaton evolution 22 times, you'll get back the identity operation. So the 22nd power of the cellular automaton function is the identity. And for these gliders, it's the cellular automaton operation composed with a shift will be the identity one. So so in a sense, what you're asking for is if you think of the cellular automaton, it's some kind of operator Diophantine equation or something. You're asking, does the or you can think of it as something like in group theory or something where, does this operator raised applied 22 times turn out to be the identity operator with these initial conditions. So those are sort of analogies, but this idea that you can go for 25 billion cases, not find anything, and then suddenly something pops out, that's just kind of a weird phenomenon. And it's I don't know what it's sort of reminiscent of the idea you do. Again, it's only a metaphor, but you do particle physics, and you do what is it these days? I don't know. I haven't been following particle physics enough, but it used to be the case that there were 10 to the 12 particles per bunch in an accelerator. So every time the beams cross in a colliding beam accelerator, there would be the possibility for 10 to the 12 particles to interact with it. Maybe 10 to the 13 by now is the number of particles. And so, of those, some small fraction actually interact. Some even smaller fraction produce, I think there's a couple of events per intersection, per beam crossing. Maybe if they're more than that, it's kind of a mess, but it's hard to disentangle the effects in the detector. But then, some of them will have, high momentum, high transverse momentum, and some of those will have top quarks in them, and some of them will have Higgs particles in them. But those are all rather low probabilities, and it's kind of similar to what happens here. But with low probability, you get, if you pick a random initial condition, with low probability, you'll get some exotic particle coming out. It's kind of intuition building, I would say, because among other things, to take the analogy further than it probably deserves to be taken, in particle physics, the consistent assumption for the last 100 years has been that in particle physics and in quantum field theory, the only things that come out are particles. In other words, the only interesting excitations of a quantum field that one can start looking at are particles. Now, there are other examples where there are solitonic things and there are other kind of solutions to quantum field equations. But, the thing that could happen, the really exotic thing that could happen is, you do your particle collision and it turns out there is essentially a solution to the equations of quantum field theory that isn't just a periodic, that isn't just the equivalent at infinity of a plane wave, which is how particles are always approximated, but it's some much more exotic, bizarre thing. That would be a totally weird possibility that nobody kind of saw coming. I mean, I think, my general feeling about quantum field theory is that it is, so when you do quantum field theory, the classical approach to quantum field theory is somewhat an oxymoron, but by the time it's 100 years old, it starts to seem kind of classical, is that you, what do you do to do a particle experiment? You take particles that are very fast separated, you let them interact, they'll get close to each other, they'll collide somehow, then something will happen, and then you wait a while and you get a bunch of particles coming out and you detect the resulting particles. Mathematically, what happens is the S matrix, which is the thing that is the mapping from initial states to final states. The initial state is some product, effectively, of the plane waves, the kind of just simple, non-interacting waves that are particles, and that then we're getting far from the original experiment. But anyway, the thing, what happens is, so there's sort of a big lie in this whole business. So the usual statement is you have these asymptotic states where there are particles that come in from infinity, all the particles are separated. You do an experiment where you just say, I set up these particles, a bunch of protons, electrons, whatever else. They're at infinity, they're coming in from it, they're not interacting at infinity. I can set them up in any configuration I want. Eventually they'll collide. I see what comes out. That process of collision is described by this S matrix. Okay, all sounds good. Now, there unfortunately is a big lie in this whole thing, which is the assumption that you can ever make these particles be separated at infinity, because a sufficiently low energy, zero mass particle an infrared photon, sufficiently long wavelength photon, you can always have, if you've got, it can always be, you can always have these things in the initial states. So one case where this goes horribly wrong is with gluons, which are zero mass particles. And the problem is you can't, well, okay, the most obvious case where things go horribly wrong with is with quarks and gluons, because in no isolated quark or gluon has ever been seen, and probably none will ever be seen. They're always confined inside particles like protons and pions and things like that. And so if you say, well, let's do a quark-quark scattering experiment, hopeless, because you can't separate the quarks to do that. All you can do is a proton-proton scattering experiment with a bunch of, with a big soup of stuff inside that has quarks there. And so, but the really bad thing that happens, and that is when you have these zero mass particles, you can have a small collection of infrared of very low energy photons, and they can always be kind of, well, in the case, let's see, the case that I remember most clearly is the case of gluons, which is if you try and have a gluon at infinity, you always get an infinite number of infrared gluons that can be keeping up with the gluon that came in from infinity. So you never get the possibility of having a sort of one gluon asymptotic state. It will always, that one gluon asymptotic state, it will always have the possibility that it will emit very low energy gluons that will sort of always keep up with it. So you can never separate it out and have it go off to infinity and not have any anything sort of making it more complicated. In fact, what happened recently, there was this big flap with various friends of mine in the quantum field theory general relativity business. Okay, so there's a related flap which has to do with black holes and black hole entropy, black hole information, and so on. Because the big flap there is you have, okay, so first of all, black holes are a phenomenon of classical general relativity. They have nothing quantum about them. They're just a solution of the Einstein equations, which has an event horizon, a singularity in the curvature, all those kinds of good things. Well, then along came Hawking radiation, and Hawking radiation, the idea of Hawking radiation is to imagine looking at what a quantum field theory does in a background space-time that's determined by a black hole and by the space-time structure of a black hole. And so qualitatively what happens is at the event horizon of a black hole, you get, so in the vacuum of quantum field theory, you're always getting these particle-antiparticle pair production events. So first approximation, one of the features of quantum mechanics is there's an uncertainty principle that says that you can't precisely measure simultaneously the position and momentum of a particle. Okay, so in quantum field theories, quantum mechanics is all about having a fixed number of particles and just saying, what does my 2 electron, 3 electron, 4 electron, whatever system do? Quantum field theory, you say, I don't have a fixed number of particles. I can have particles created and destroyed. And so then there's sort of an uncertainty principle about particles that says you can't know exactly how many, in the vacuum, for example, you can't really know that there are 0 particles. You always get these virtual particle-antiparticle pairs that get produced and then destroyed again some small time later. But so in the vacuum, there's this sort of bubbling particle-antiparticle pair mess. I mean, the structure of the vacuum for quantum chromodynamics, QCD, is pretty much still completely unknown. It's a big, complicated mess of strongly interacting particles, and nobody really knows what it's like. But the vacuum for more weakly interacting quantum field theory is a bit easier to understand, maybe. But anyway, it consists, so it has these particle-antiparticle pairs that get produced. Well, the thing that happens if you try and set up quantum field theory in a curved space-time, like near a black hole, the qualitative physics says there's an event horizon, and you have a pair production event right close to the event horizon, and one member of the pair wanders into the event horizon, the other member of the pair doesn't. The member of the pair that wandered into the event horizon is lost, is lost, invisible to the rest of the universe. And so that is what causes Hawking radiation, because then the remaining member of the pair can escape to infinity and can never reannihilate, because it can't get back in touch with the member of its pair that fell into the event horizon. So that's kind of the qualitative explanation of Hawking radiation. But the thing that's sort of paradoxical is that if you believe in quantum mechanics, you believe in some kind of information conservation, and you believe that when you form a black hole, it shouldn't be the case that your effectively, you have all this quantum information, and it's all sort of being ground up into this black hole. The black hole there is no sort of visible sign of all the information that went into the black hole. Eventually it comes out in this Hawking radiation, which is thermal, and basically quantum information. I mean, there's a few more steps to this, but basically there's a sort of paradox that what you thought was a quantum process is that conserved information. When the black hole is formed, the information conservation all goes to hell. And so the question is why, how do you resolve this paradox? The answer has to be that somehow that information is preserved by the black hole. And I'm kind of muddling this up slightly, but the recent explanation of this whole thing is, well, actually, when the black hole is formed, there is some kind of low energy radiation that kind of hangs around in the rest of the universe, kind of carrying that sort of relic of the original quantum information that was used by the stuff that made the black hole. So anyway, the end result of this whole thing is that you can never do, if this is the case, then when you preserve the quantum information stuff, you can never effectively do a true repeatable, a true isolated experiment, because there'll always be, everything gets entangled with everything, and you'll never be able to have an experiment where you just say it's just a black hole and a particle. It will always be, oh, well, actually, to be realistic, you have to have all of these low energy photons and so on that were hanging around forever. And, in a sense, one of the axioms of science, as it's been done for the last 300 years or so, is that it's possible to do experiments, controlled, isolated experiments. And this kind of gives a lie to that idea, because in order to do controlled, isolated experiments, it better not be the case that in order to preserve quantum information, that no two experiments can ever actually be isolated, because in the process of conserving quantum information, there's this little, low energy photon that has to hang around to kind of carry the quantum information from one place to another. And that's sort of from a philosophy of science point of view, that's kind of a bad deal, that you have to, if you can't isolate an experiment, you have to kind of, then you can't really do science as Baconian kind of repeatable experimental science was supposed to work. You just can't do it. And then the only thing you can do, which is really a screwy situation, is if you want to model the universe, you're stuck with then you have to model the whole universe. You can't break it into pieces and say you can model this piece separately from this piece and so on. And that's really bad because of computational irreducibility, because then you're stuck, because the whole universe is like, the only way you can model the whole universe is by having something that's pretty much just like the whole universe. And that's kind of a bad story for science. And we kind of have to hope that there's enough sort of pockets of computational reducibility in the universe that we can kind of identify, that we can sort of recognize phenomena that can be modularly plugged and played. I mean, it's not, this basic point about can you make isolated systems is the question of whether there's modularity in the structure of the universe, or whether there's some, irreducible kind of little threads that connect different parts of what happens in the universe. And it's, anyway, I don't know the answer, but I think it's interesting to, these things like these simple cellular automaton models are a nice place to sort of experiment with one's thinking about what's going on. We don't have the analog. There are lots of things we don't have the analog of. In these network systems, we do have the analog of space-time curvature and all kinds of structure like that. The problem with these network systems is we don't want to know what the analog of these particles is, because the only way we know to get get sort of stable structures in network systems is through some topological stability mechanism. And the only example of that we know is nonplanarity in graphs, and the phenomenon that if you have nonplanarity in a graph, there's always a knot of kind of particular. Okay, so any graph that isn't planar always contains one of these K33 subgraphs, and that's a theorem in graph theory from like 100 years ago, maybe 1920s, due to a guy called Kuratowski, and that's it's a fact about graph theory. Any non-planar graph has a K33 subgraph,
Okay, fine.
The problem, what's that?
Okay, fine.
Yes, that is correct. If you're absolutely right, or K5. The K33 case is if you have a trivalent graph, which is what I've been mostly concerned with. But you're absolutely correct. The case that is, but what I've been interested in is, let's say, so if you have an evolution rule that preserves planarity, then these K33s or K5s are the only things that the only sort of surviving lumps. But if you have a rule that is more complicated than just preserving planarity, we have no idea what the conserved objects are. And my effort to ask the world's sort of leading graph theory folk has led to statements like, ask again in 100 years, which is that graph theory is far from, in its current development, is far from being able to get these generalizations, which is kind of disappointing. And it means, it means one is kind of on one's own, sort of as a, it's often the case that physics drives, need for more mathematical results. And this is a kind of, we're on our own and need kind of some physics approach, but I mean, I don't know how, I simply don't know how to do it. But that's the problem is, in this case of finding particles in cellular automata, it's a lot easier because this notion of, it's, in the case of the network, there is some sort of background activity in the network. In the case of this sort of, the background here is very straightforward. In the case of Rule 110, for example, the background is a little bit more complicated. It's a periodic thing. In the case of these networks that we thought about for space-time, I doubt that the background is anything simple. Although, actually, I don't really know that. I mean, it's possible that there's some, I'm looking at Maxime here because he's looked at these network systems a bunch, but I mean, it is conceivable that there is some sort of something sort of periodic that it's not conceivable, because the fact is that that background network has to be kind of reproducing something like the quantum gravity vacuum, and it's really just not plausible that that's just some simple periodic thing. If it were, it would certainly fail to have all sorts of properties. Somebody on our live stream is commenting that you can argue that modularity is something that can be proved using from renormalization group and effective field theory, or that you can show that quantum field theory would prove that essentially that as you separate 2 points, that the correlation function, which sort of tells you the correlation between two places in quantum field theory, would fall off as some power of the distance. Yeah, maybe so, but the way this works, well, I don't know I think one of the problems about some of this quantum information stuff is that it ends up being rather in the nature of medieval science, where you're arguing about, irresistible forces and immovable objects, or, angels on heads of pins and so on, because it's like, did the information get conserved? Well, we just need a tiny bit of information conserved. It's a zero, and so just knowing that some correlation function falls off doesn't really tell you that much. But I think the whole question of effective field theory, I mean, this whole, the whole business from, okay, so there are a couple of comments to make. I mean, one comment is, in the case of these cellular automata with particles, it would be interesting to see whether there is a renormalization group type approach that could tell you something about large-scale structure without looking at the details. I'm somewhat skeptical. In the case of these network systems, then absolutely one has to have an effective field theory, because one is asking, whatever should correspond to actual quantum field theory as we know it in the standard model of particle physics or whatever, must be an effective field theory relative to all of the microscopic, flappings around of the underlying network.
Out of interest, is it conceivable that you could have sort of endlessly growing non-planar pieces of the network multiple space, analogous to these situations where you have two colliders colliding in CA and it produces some persistent structure that goes without bound?
Okay, so the question is it possible that the network could sort of tear itself apart? Or, for example, that the network could develop a piece. This network has no fixed dimension of space and time, well, of space at least. And so one possibility is that you could have a little piece of network that is not effectively three-dimensional, for example. And one might think that in the early moments of the universe, that the network might be highly connected and effectively very high-dimensional, and that as the universe sort of expands and cools down, so to speak, that the network would then sort of decay to being three-dimensional, and that might solve various kinds of inflation and homogeneity problems for the early universe. But the question is, could you induce something which... So one would suspect that in things which are like particles, there is a sort of lump of network that is a little bit like a higher dimensional lump of network that's more connected than the typical. But then the question is, could there be a large region of highly connected network? And actually, okay, so when I did this little work on this Arrival science fiction movie, I had this kind of spend an evening and invent a scheme for interstellar propulsion. And so I came up with a little bit of a scheme that involved basically, it's not very realistic because, actually inventing, interstellar propulsion, A, will probably take more than an evening, and B, we're kind of far away from the physics of that. But sort of the idea there was, could one, by some weird mechanism, induce something which is a large-scale, higher dimensional? Because if you want to get from here to there, then if you can, then the bad case is you just have to go through the three-dimensional structure that gets you from here to there. If, on the other hand, you can induce something which was higher dimensional, you'd have the possibility of getting from quotes here to there in the three-dimensional space with less graph steps than if you had to go through the whole three-dimensional thing. And so that was kind of the concept of that spacecraft. But more seriously, I mean, it's absolutely not clear. I mean, one feature of general relativity is that it does assume, even in the case of, singularities in space-time, it's still assuming that everything is, 3+1 dimensional. And that might just be completely wrong. I mean, clearly, if you have a partial differential equation, which is what the Einstein equations are, and that partial differential equation says that there's an infinite value of one of the parameters in it, then that partial differential equation doesn't tell you what's going on. I mean, the analogous cases in fluid flow, in the Navier-Stokes equations for fluid flow, so in subsonic flow, the sort of definition of subsonic flow is there are no shocks, there are no singularities in the velocity field for a thing. But if you have a plane that is going at supersonic speeds, then the definition of supersonic is, in a sense, faster than the speed of sound in the gas, which means that there will be a shock front where there's a singularity of some kind in some parameter associated with the things described by the differential equation. And the problem in practice is that those singularities so it's usually a singularity in the derivative, but there is a singularity. How does this work? The width of the shock is determined by the Knudsen number, as I remember. Somebody here probably knows this physics. But it's determined by a ratio of the mean free path. So there are various parameters. So in the Navier-Stokes equations, you assume you have a continuum fluid. But in fact, the fluid is made of molecules. And one of the things about these molecules is that there's a certain mean free path. There's a certain distance the molecules go before they hit another molecule. And in a typical, in air, in typical sort of situation, that mean free path is tiny. The problem is if the sort of shock front implied by these equations is narrower than the mean free path, then very bad things will happen, because then the continuum description of the fluid is not going to be correct. If you say, but in this tiny, thin region, there is it matters what the then's going to matter that there are molecules there, because you can't get a continuum fluid if you haven't had enough collisions between molecules. So in practice, things start getting really wild at around Mach number of 5 times the speed of sound, and they get really wild. I think by Mach 5 you're in hypersonic flow, which means that it really matters what the molecular structure is. And that one way that happens is now we're probing the details of my knowledge of fluid mechanics. But basically what happens is the gamma, the adiabatic index, which is the ratio of the specific heat constant pressure, specific heat to constant volume, which is determined by the number of degrees of freedom. It's like 5/3 for a monatomic gas. Is that right? It's determined by the structure of the gas. It's determined by the molecules. And the gamma starts mattering in the actual computation of the flow, because it affects the structure of these shocks. A piece of trivia I recently learned a few days ago is that the space shuttle enters the atmosphere at Mach 25. And where this effect of these shocks is really big, but actually it has a different thing going on, which is the shocks are so strong that they ionize. The air gets ionized, which is why why there's this whole sheath of ionized gas, which prevents radio communication, blah 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 blah. But apparently the whole sort of physics of how that works was not readily simulatable, and was actually gotten significantly wrong. And for the actual space shuttle when they actually tried it out. But the main point is, in the Navier-Stokes equations, that's all irrelevant. But the main point is, in the Navier-Stokes equations, a sufficiently strong shock reveals the inadequacy of the Navier-Stokes equations, and kind of everybody knows that. You have to look at the underlying molecular structure in order to find out what goes on, for example, in hypersonic flow. So in general relativity, you have the same situation. There is the equivalent of, it's not quite a shock, but it's the singularity in the curvature tensor. And people just say, oh, well, I guess there's a singularity in the curvature tensor. And it's probably something which reveals the fact you have to know what's happening underneath the equations of general relativity. And one of the possibilities, which will be interesting to investigate, and I think is that maybe the true equations don't preserve a fixed number of dimensions of space-time. And that if, that the question will be, can you regularize? So one possibility, as I think about it, is some kind of, so in particle physics, there's a common technique called dimensional regularization. So when you compute, okay, so boy, we're way off track, but anyway, it's perhaps amusing. So one of the big problems of both classical electrodynamics and quantum electrodynamics is the presence of infinite self-energies. So if you have a ball of charge, and the formula for the effect, so you have a sphere, a metal sphere, and it's charged, there'll be a certain amount of energy because the pieces of the sphere will repel each other because they're all charged, and like charges repel. Okay? As you reduce the size of the sphere, the amount of repulsive energy goes to infinity, like 1 over r. So that problem, if you want an electron and it's of 0 size, then it will have, and it's a classical electron, it would have infinite self-energy. Okay, so you might say, well, it's all going to go away when you deal with quantum electrodynamics, but it doesn't, because then you have these Feynman diagrams where you have an electron going along, it emits a virtual photon, the virtual photon is reabsorbed by the same electron, and that Feynman diagram has an infinity that comes from an integral that you can do in momentum space and so on. But anyway, the infinity is basically the same infinity, okay? And that's what causes and so there are these infinities in quantum field theory that are associated with things like these self-interaction loops and so on. Well, the big deal of quantum electrodynamics is that there are only 3 different weird infinities that show up. And you can always just say, well, even though the electron has, given a bare electron, it would have infinite self-energy. But how do you know that the original electron didn't have minus infinity mass? And all you're doing is adding on. You can never see an electron without its cloud of virtual photons and things like this. And so you can it's like the bare electron mass might be minus infinity. You add plus infinity, which comes from the self-energy, and you just get 0.511 MeV, or whatever the actual mass of the electron. And you say that's a total kludge. And the people like Dick Feynman, who invented this renormalization idea, thought it was a total kludge. But the point is that you only have you only end up with these three different sort of independent infinities in quantum electrodynamics. And so you can basically, the whole theory can be worked out in such a way that if there were an infinite number of unknown infinities, you wouldn't be able to say anything. But given that there are only three, you can sort of just factor those out of the things you have to compute. And the renormalization group provides a way of doing that, which we could talk about. But the thing that the problem. Okay, so what happens? So the reason quantum gravity is such a big deal is because the naive way to quantize gravity, which would be instead of having photon interactions, you have graviton interactions. The graviton is you can make a weak gravitational field can be thought of as something like an electromagnetic field can be thought of in terms of virtual photons. A gravitational field can be thought of in terms of virtual gravitons. A graviton is a happy little particle. Photons have spin 1, gravitons have spin 2. It's fine and dandy. The only problem is that when you work out the interactions between gravitons, you get a theory which has an infinite number of infinities in it. And that's why sort of quantum gravity has been hard to deal with, because it is not renormalizable in the same way that quantum electrodynamics or QCD are renormalizable. Anyway, having said that, when you actually do computations in QED or QCD, a good technique for doing them is a thing called dimensional regularization. So when you compute these various integrals and so on, you get a bunch of infinities. But in order to get, you have to you have multiple infinities and they cancel each other out. And you have to sort of manage the cancellation of those infinities. The common way to do that, which I guess I was involved in kind of somewhat promoting back in the late 1970s, was this technique called dimensional regularization, where you basically assume that instead of there being 3 + 1 dimensions of space-time, there are let's say 4 minus epsilon dimensions of space-time. And so then you do these integrals over 4 minus epsilon dimensional space-time, and those integrals happily converge. In 4 minus epsilon, when epsilon is non-zero, the integrals are finite, everything's happy. And then at the end of the whole computation, you take the limit epsilon goes to 0, and you supposedly get the right answer. And that's a method for implementing some of this generalization stuff. So there are various comments on the live stream here. Let's see. That's a comment that an example of the theory with no fixed dimension would be causal set theory, but good luck showing it has a continuum limit. Yeah. Okay. So, but just to right, that's true. So my question would be, if you think about dimensional regularization and you think about what does general relativity look like in dimensions other than 4. So general relativity is, it's full of, so you have the metric tensor, which determines distances in space-time, and then you have the curvature tensors, which determine curvatures, like you go around a closed loop, do you get back to what's the angle deficit when you go around a closed loop and things like this. And the big creature that you get is the Riemann tensor, which is this four-legged animal, four-legged tensor at least, that has, anyway, the question is, how can you set up, so in D dimensions, for different D, you get different structures for things like the Riemann tensor. And I have no idea how so for example, tensors tend to have a fixed number of legs, and they tend to have a fixed number of degrees of freedom. And the question would be, could you have a continuous dimension? Could you have a definition of things like the Riemann tensor with with a continuous dimensional? In other words, how do you set up the machinery of general relativity for tensors that have a continuous dimension to them? Because even numbered dimensions are different from odd numbered dimensions. In particular, boy, this is getting kind of technical, but these things called the Levi-Civita tensors, which are the totally antisymmetric tensors, behave differently in even dimensions and odd dimensions. There are enough physicists that somebody knows how this works. And so I don't know how you interpolate between dimensions with continuous dimension, but it would be interesting to investigate whether if you sort of regularize general relativity. So here's the concrete question. Imagine a general relativity that has been regularized by having a non-integer number of dimensions. First of all, what happens to the singularities that exist in ordinary general relativity? I don't even know what 5-dimensional black holes look like, though I think those have been studied. But the question is, if you look at like the Schwarzschild solution to general relativity, and you say, assume space-time wasn't 4-dimensional, but was instead, 4 minus epsilon dimensional, what does it look like? Anyway, it's a good exercise for, that's one of those things where one says, it's an exercise, but the exercise might take 100 years. But because I think it's technically difficult, but it's.
Don't you already get sort of effectively higher dimensions in where you have stress energy tensors where the strong energy condition is violent, for instance, in inflationary model. The conformal structure that you get out is, I think, formally more than 4 dimensions.
So the claim being made is that when you mess around with the stress energy tensor and you violate the various energy conditions of the stress energy tensor, you effectively get different dimensional space-time. I don't think so. I think all it affects is it's like adding cosmological terms and things like this. I think it affects the structure of the Einstein equations, and it affects the energy conditions of things about if you have matter, what is the equation of state of the matter? So in particular, if you have a gas and has a certain density, what is the pressure of the gas? And so the two cases that people really think about commonly are dust, which is pressure 0 and some energy density, and the photon gas, which is pressure equals 1/3 of energy density. There's some factors of speed of light, which I forget. And so the question is, if you are going to form a black hole, there are certain singularity theorems in general relativity that say it's inevitable to form black holes and so on. If matter doesn't, if you don't have a weird energy condition for matter. Now, of course, in the world of physics as it is, P equals minus rho is, if I'm not mistaken, that's the dark matter equation of state. Yeah, that's dark energy, right? P equals minus rho is the dark energy equation of state. So, totally exotic, but supposedly necessary to reproduce current cosmology results. Okay, we should stop. It's time for dinner, and for people who have been on the live stream, we strayed pretty far from our space coin of several hours ago, but hopefully people had fun.